Okay, we're now going to take a look at radians, arcs, and sectors and see how trigonometry also works on circles. Up until now, you've probably been working primarily with degrees, but the problem with degrees is it's somewhat meaningless, actually. There's no reason they picked 360 other than it's easily divisible. It's related a little bit to the length of a year and how long it takes the Earth to go around the sun. But there's no real reason beyond that of why. But we're going to take a look now at radians. We'll have to use both as we go on, but a radian has a direct relationship to the amount you go around a circle. You can probably see the word radius and radians are relatively similar. One radius is one radian if you subtend that length along the circle. So this angle here would be 1 radian. And because of the circumference of a circle, you get in one full circle that there are 2 pi radians, just like the circumference. And in half of one would be 1 pi, or 180 degrees. So if you wanted to convert them, you could say, well, just a fraction of my 180 degrees of pi, those are the same, is going to be an equivalent fraction, and convert them that way. You could also, of course, use 2 pi and 360, but make sure that you're setting up equivalent statements. Often radians have a pi in them instead of multiplying them out, but they don't always. So you really need to be clear when you're using degrees to make sure you have a degree symbol, or otherwise it would technically imply radians. So radians, pi over 4, you can think of these nice things. Well, here's pi is 180 degrees. So pi over 4, if I were to split this into quarters, would be 45 degrees. You could also, though, substitute this into this equation here and say you have, okay, well, radians, pi over 4 radians divided by pi is equal to some number of degrees over 180 degrees. Pi's will cancel. You have 1/4 and multiply it by 180, and you get 45 degrees. And you can do the same thing going back the other way. You could even, or try to think of this in fractions of this half circle. 120 would be 2 60-degree pieces. So if I split this into thirds, it's 2/3 of a pi, because it's 2/3 of the way to 180 degrees. Or you could put this in and say some number of radians over pi radians is equal to 120 degrees over 180 degrees. Simplifying this, you're going to get 2/3 here, and multiply by pi, you get the radian measurement. I'm going to do the next problems first in degrees, but we'll probably look at them only in radians and see the relationships. Sometimes it makes sense if you're so used to working with degrees to do things in degrees, but make sure you don't write them down, even if you're kind of thinking through them in degrees, because they may take points away for not being able to work in radians. So an arc is a piece along the circumference of a circle, a fraction of a circumference. You have the minor ones, which is the closest way to kind of walk along a circumference from one point to another. That's always assumed. Or a major arc, which would be the longer way around. If it is the major arc, you're going to have some other letter in here to indicate which direction you're going through. So if you want to calculate the length of this minor arc, how long do you have to walk from A to B? The shorter one, well, you know that's a piece of the circumference. And remember that the circumference of a circle is 2 pi times the radius, or you could say pi times the diameter. So 2 pi times 5, or 10 pi. But you only have a part of this. So the arc AB is a fraction of this circumference. And if you're working in degrees, well, it's this much of the fraction of the circumference. This is more of a reminder. Remember this. But it's a fraction of that. And if you were to reduce this, well, if you find the greatest common denominator, I can cancel out the zeros. 536 times 10 pi, or 5036. And of course, you can simplify these as well. Divide this by 2, 18, and 5. So 25 over 18 pi's. So that would be the length of this minor arc here. You can usually leave them with pi unless it says to find the exact value, and then it's just a matter of putting that into your calculator. Don't use 3.14, or anything like that. However, because this is a circle and it makes a lot more sense to use radians for this, we usually will use radians for these circle measures. And we may also use radians a lot for the functions in trigonometry, or even for triangles in trigonometry as well, because of the way that this simplifies. So again, if you look at this minor arc and you think of some fraction of the circle, right? So 2 pi r, thinking back to what we just did in degrees, this is the circumference, and you have a fraction of the full circle. We used 360 degrees if we're working with degrees, but remember that's equivalent to 2 pi's. So it works out to be very, very nice when you're working in radians here. So if you want to find the minor arc, I can call this L. I was just doing it to show you the similarity to the last problem. In the figure below, here's an example. AC is the diameter of the circle P. Remember, that's twice as long as the radius. The length of PC, so just this radius, is 25 units. What is the exact length of BCA? So that's then indicating a major arc because you're going through C. So there are a couple ways to do this. You could find the full circumference of the circle and then take away the part you're not counting. Or you could think of how big this angle is right here, which is what I'm going to do, and use that. So the length is theta times the radius. Theta here, remember that the full circle is going to be 2 pi, but we don't want to include this amount. So 2 pi minus 3 over 10 pi, and the radius is 25. Okay, 2 pi, in order to subtract fractions, you need to make sure you're using a common denominator. So 20 over 10 pi minus 3 over 10 pi times 25. Then this is relatively simple. So 17 pi's over 10 times 25. And I'm going to reduce these, divide. And 17 times 5 is going to be 170 divided by 285 over 2 pi. And it does say find the exact length, so you wouldn't want to put this as a decimal because it would no longer be exact. Okay. Much easier when you have the angle given in radians. We can do a very, very similar thing when we have a sector. So a sector is, instead of the crust of a pizza, like the length of an arc, it's the area of a full piece of pizza. So find the area of the shaded sector. If you were looking at this, this is a part of the full circle. And if you're working in degrees, then you would say, well, it's a part of the full circle of the full area, and that's the area. So 80 degrees, in this case, 360 degrees times pi. OA is the radius, always check that. Sometimes they give you something else, squared. And then as you simplify this, you're going to be able to quite quickly, just for the sake of time here though, you can put this into the calculator. 144, this just gets messy. I don't want to do it. So 80 over 360 times 144 times pi, so 32 pi. And this would be, we don't have any units given, so units squared. But the same thinking when we're using radians is going to reduce in similar ways to this, where you have a very simple equation given to you. It doesn't reduce quite as well because you still have the pi r squared. You just have your theta, 1/2. Something went, this should probably be theta here. Let me make sure I've derived that correctly. So if I work through here, before you write that down, the area is a part of the full circle times pi r squared. Oh, okay, where we cancel out the pi's from top and bottom, and we have 1/2 theta r squared. There we go. These are also in your formula booklets. It doesn't give the warning that it's only in radians, though, so you do need to make sure you remember that. And 1/2 theta is 2 pi r, or 2 pi over 3. Sometimes, again, you'll see this reduced to rad, if just to be explicit, but you don't need to, times 450 meters squared. This is absolutely a calculator problem with the 450 squared. And again, it wants the exact value, so you will need to keep it with the pi. 67,500 pi units meters squared. Okay, pretty straightforward.